Hello everyone. Hello everyone on YouTube as well. I am Aniruddha and today we are meeting for the fifth time in this course on measure theory. So today's topics include outer measure, Lebesgue measurability of sets, and one of the examples that was included in the assignment. I thought it would be better to include it in this session. So yes, uh, hello Robin. You had some questions, right?
Yes, Aniruddha, I had some questions. Thank you.
Mhm. So you can ask me.
So the questions that I had were so I think it's the exercises in lecture 4.2. I think so there were about 3 or 4 exercises. If you can show me at least 2 or 3 of them, just to
Uh, Actually, I don't have the questions with me. So could you just tell me what are the questions?
um, let me just see. I think it was basically the outer measure properties. So one was let A be the let A be the algebra uh,
Mm-hmm.
of subsets A that are subsets of R, such that
Okay.
A and A complement are both finite.
Oh, okay, okay. So it has a proper definition, is it? Mm-hmm.
Yes,
A or A complement is finite. Yes.
yes.
What was the question here?
So the question was, show that a measure
Mm-hmm.
um, mu A is equal to 0 if A is finite or countable, and show that mu A is equal to 1 if A complement is finite. That I understand the logic, but I just don't know how the derivation works.
A complement is finite. Oh, so right. So to prove this is a measure, what all things do we need?
Uh, kind of. So the first one would be it has to be finite.
What should be finite?
The measure should be finite.
Yeah, this is finite, right? Because you take any set inside this algebra, the measure is either 0 or 1. So
Yeah.
this is a finite measure. But see, to prove it a measure, we require two things. One is the measure of empty set should be 0. And the other
Ye-
thing is that it should be countably additive.
yes, yes, that's what I was going to say. So it has to be finite. The measure of the empty set has to be 0, and it has to be countably additive. Yes.
Correct. So measure of empty set is finite is immediate from the definition, right?
Yes.
Would you agree on that? Because empty set is finite, so measure of empty set is 0, which is what we require. So the only thing we need to check is countable additivity,
Yes. Yes.
right? So let us start with a sequence of sets inside A, which are mutually disjoint. So AN intersection AM is empty. Now
Hmm.
what do we require? We want measure of this disjoint union of ANs to be equal to this sum.
Yes.
Okay. So right now, see out of this, if suppose all these ANs are, or rather, if this whole union is finite, then what can we say? Although, are you sure that this is a measure?
That's what the professor said.
Or is it?
Yeah.
Because
He says that
what?
you have to show that mu is a measure by showing that mu is countably additive. So
For
the
this one, is it?
yeah
Because here there is a small issue that comes to the mind. Suppose I take AN like this, singleton ends. This is indeed a subset of R, right?
yes,
And
but the
this is
measure of
also
this would
inside
be
this
zero.
algebra.
But the measure of the singletons would be 0, right?
Measure of singletons would be 0. What I am saying is, what about the measure of this union? Because
That
this is a
that
disjoint union, right?
Yeah, that would also be 0, right? Because if it's a union of if
Acha,
it's a
acha. Oh, yeah. Sorry, sir. Actually, the thing is, unions need not be inside algebra, right? We have to assume one more thing, that this is true whenever this union of AN is inside it. Correct, correct. Yeah. So, what were you saying?
so if A is countable, if A is the set of all singletons or rather, if A is a singleton of which is a subset of R, then the union
Right.
of all singletons is going to the measure on the union of the singletons is going to be 0, because the measure of on a singleton is 0, which basically means if I took union over the singletons, and
Yes.
if I applied a measure, then that's going to be basically uh, countably additive uh,
Yes,
measures.
but that is the assumption you are taking, that the measure is accountably additive. But that is what we want to prove, right? We
Yes.
want to prove that measure is countably additive. Okay. So, okay, let us try to do this. Suppose that this union is inside A. Now there are two possibilities. Either this union is finite or its complement is finite, right?
Yeah.
So, sorry. So if this union is finite, the only way this can happen is that all of these ANs are finite. AN is finite for every N, right?
Yes.
So therefore, what about the measure of this union? By definition, it should be zero.
Yes. Yes.
But this summation of new ANs, this is also zero, right?
Yes.
So at least in this case, these two are equal. Do
But
you agree?
if I took the complement of this, right?
Right. Now we have to check the other case. What
Yes.
happens when this union, the complement of this union is finite? Right? So if this is finite, then so one thing we know is that this measure of this union, this is equal to 1, because that is the definition of the measure for us,
Yes.
right? Okay. Uh, Now, right. So, acha. But then from here, how do we say that this sum is also 1, right? This we need to check.
I think what the professor said was to show that 0 and 1.
Right?
So he's defined mu A is equal to 0 if A is finite, and mu A is equal to 1 if A complement is finite, which is basically
Correct.
A is infinite or uncountable. So if
Ah, yes.
this is where I'm stuck as well, because I'm trying to understand how if I applied measure, um,
Mm-hmm.
and if I took summation up to infinity, is it
Right.
bounded to 1? Is the upper
Yes, that is what we have to prove here. That is exactly the proof. If we are able to prove that it is bounded by 1, then at least one of them has to be uncountable, right?
yes, but
So
but I think um yes, because the measure has already been defined as mu A is equal to 1. So now we have to show that mu summation of all the mu A n's from 1 to infinity has to be 1 as well.
correct, correct. And for that, actually, what is sufficient is if we are able to prove there is exactly one AN whose complement is finite, then we are done,
Uh,
right?
can we use the
Yeah.
outer measure property?
Which property?
The outer measure property, instead of just using the measure property, can we use the outer measure property?
But for outer measure, we require a measure first, right?
Yeah.
So, outer measure is only given once we have a measure on an algebra, then we can extend it to all subsets.
Yeah. Yeah.
So that actually, I think this is why this example was given, right? After this, there was one another exercise to check the outer measure about this,
Yes, exactly.
right? Yeah, I remember. Okay, okay. So actually, the thing is, see, one of the claims that we can make, at least one aim is, or rather, at least one aim complement is finite.
Hmm.
Okay. So why is that true? Because if all the ans are finite,
Hmm.
if all ans are finite, then what will happen? Uh, then this basically either this countable union, this
It's
is
going to be
finite
finite. Yeah.
or countable. But the first case we have already seen, right? This is already done. So and this cannot happen since union A and complement is finite. I know, and complements of countable sets in R they are not finite.
Yeah.
So therefore, at least this claim is true. At least one of the A n complement is finite. So suppose it is A n naught. Okay. Now what? Right, right. But then we have to prove that no other A n complement is finite, right?
Anirudh, can you can you explain this step again? So we are showing that at least one of the an complement is finite.
Uh-huh. Right, right. So what I'm claiming, this is the claim, right? So suppose this is not true. So if this is not true, then all the A n complements are not finite. But since A n come from this algebra, if A n complement is not finite, then A n has to be finite.
Can we just show that this is an algebra first? Because we get
This is
showing that this is an algebra would be easy, but then we can start we can probably start applying the measure function on top of the algebra and build on from there. The only issue that I'm having is I'm actually trying to understand how
uh-huh.
can we how can we just, let's say, bound it to one rather than, because when I'm taking the summation, it's like, well, if I take summation,
Yes, yes. Yeah, that is the concern, right? That if what happens if all these A n complements are finite, then there is going to be a problem.
is there something that the professor said about the summation being bounded to one as well? If the individual, uh,
No, I don't recall that any such thing can happen because in general, even countable subadditivity we may not have for those things. Could you tell me which lecture it was in? I
it was 4.3, outer measure and
outer measure
outer
and its properties.
properties. Yes.
Right, right, right. So, hmm. Oh, right. So there was this one thing.
He used the
So
singleton
this is.
theory as well, which is if A is countable,
Mhm.
the union, let's say that A is the set of all singletons,
But
then the
yeah,
union
yeah,
of,
that is to
yeah.
check the outer measure, right?
No, he used it to check, uh, to first check the measure, and then
To check the
he
measure. I don't know.
he
I don't
first
think
used.
he must have used it to check measure.
So I think he said let A be the set of all singletons. Then if
Mm-hmm.
you take if you take a union, because singletons are countable. If you take a
Yes, yes. Okay, now that you see it, actually, yeah, this is quite easy. See, we have to check that this is a measure, right? So let me just
yes.
erase all this. These are all really thoughts. Okay. See, this one is fine, right? That if union of A n is finite, then both the things are zero, therefore they are equal.
Yeah.
Now, let us observe one thing. Is R complement finite? It is, right? Because R complement is empty set.
Yeah.
So this measure of R is going to be equal to 1.
Yes,
Correct?
yes.
Okay.
By
Now,
the definition, yes. By definition
right.
of, yeah.
And see, whatever we did here, acha, but okay, that will require one more thing. This is one more thing. Can we prove that mu is mu is finitely additive? Can we prove this?
Mu is finitely additive.
That means if you take two disjoint subsets and their measure of their union is equal to the sum of their individual measures.
Yes, I think we can do that if we took
We can
a,
do that, right?
yeah,
Because
if we
then
took
mu of
disjoint intervals, right?
I couldn't hear you.
If we took disjoint intervals, if we
Yeah,
took
but
two,
intervals are not finite and complements of intervals also are not finite, right? See, when I say that A or A complement is finite, it means it is a finite set.
oh, okay, yes, yes, yes.
Yeah, yeah, yeah. So these intervals are not inside this algebra.
Okay, fair enough.
So see, if again if this is finite, then both of them are finite.
Mm-hmm.
Then both like this is zero and mu a individually are also zero. Correct.
Yes.
On the other hand, this A union B whole complement finite would mean that yeah, this is again in terms of intersections really. Okay. So let us see. This is finite. Hmm.
Would this be finite or would this be infinite?
No, no. See, either A union B is finite or A union B complement is finite, right?
Yes.
So when A union B is finite, that thing is done. We got the equality.
Yes.
Now we have to prove when A union B complement is finite, what happens?
A union B complement is finite, which is complement intersection B complement.
Yeah, but from here again,
If they're disjoint, their
right.
their intersection is going to be the null. Their intersection is going to be the null set.
But A and B are disjoint doesn't mean A complement and B complement are disjoint.
Yes, exactly. That's what I was getting to,
Ah,
which is not
so,
the null set.
yeah, so what happens? Yeah, so one thing is at least one of them is finite, right?
Yes.
No, no, not at least. I mean, either A complement or B complement is finite.
Yes.
Either A complement or B complement is finite. Because if both A and B are finite, then A and B is finite, so its complement is not finite. Okay. So now what we have to do, we have to prove that if this is finite, then this cannot be finite.
Yes. Yes.
But then why is that? So if both of them are finite, then what happens? Then their union is finite. Okay. So
Anirudh, would it be possible to take the union of A complement intersection B complement?
union of what?
If you took a no, sorry. A complement intersection B complement, and they then take a complement over them.
Yeah, but that would just give us a union B.
Oh yes, that's just going back. That's just,
Right,
yeah.
right. This is so let us take A complement union B complement. This is equal to A intersection B whole complement, right? And if
Yes.
both of them are finite, then this is finite. But it doesn't really give us any. Right. So see, so if this is finite, yeah, but A intersection B is empty, right? That was our assumption.
Yes, because they're disjoint. Yes.
So we are saying that R is finite, which is not possible. Correct?
Can you say that again? So we're saying
Yeah.
that
So
A. intersection B is null.
So
So because that
what we are saying is that A intersection B complement is finite.
B complement is finite. Okay.
Okay, but that cannot happen, right? Because A intersection B is empty and empty complement is all of R.
Yes. Which is a contradiction because R cannot be finite.
Correct. R is not finite. So therefore, whenever A complement is finite, B complement is not finite, and whenever B complement is finite, A complement is not finite.
Yeah.
So even in this case, measure of A union B, this is 1 because its complement is finite, and this is equal to measure of A plus measure of B. Because exactly one of them is 1, the other is 0.
So
Correct?
can you tell me about how we got to A, measure of A union B is equal to 1?
Yeah. So, okay, did you understand that if A union B whole complement is finite, this implies that either A complement is finite or B complement is finite. Is this step clear?
Wouldn't it be A complement union B complement?
No, no. Why would we take A complement union B complement?
You're saying that A union B complement is finite, which implies that. Um,
Actually,
okay.
yeah.
Yes. So sorry. I got it
Uh,
confused. Yes, this step is clear. That this
this
step is
step is clear, right?
yes.
Now, see, then since one of them is finite, I am also proving that claim is that exactly one of them is finite. That means they cannot be finite together.
Yes.
And why is that true? Due to this calculation. That if both of them are finite, then their union is finite. So, the union of A complement and B complement is actually the complement of their intersection. But
Yeah.
intersection is empty, so we are claiming that R is finite, which is not possible.
Yes.
So therefore, exactly one of A complement or B complement is finite. So without loss of generality, assume that A complement is finite. So measure of A complement is 1, measure of B complement is 0.
Yes.
Sorry, the other way around. Measure of A is 1 and measure of B is 0.
Yes.
And therefore measure of A plus measure of B, this is 1.
Yes.
On the other hand, measure of A union B is anyway 1, right? Because A union B complement is finite, that is what we started with.
Yes.
So these two are equal even with this case.
Oh.
Right?
Sir,
Uh-huh.
sir, here you show that A union B complement is finite, then either A complement is finite or B complement is finite.
Right.
So, two infinite sets and their intersection can't be finite.
Yeah, it can be, but actually the definition of algebra is such that either A has to be finite or A complement has to be finite.
Okay.
That is, this implication is due to the definition of algebra. Okay, so Robin, is this clear?
Yes. And then taking the infimum over this, that's what gives us the outer measure, right?
Yes. So
Yes.
what you can do to check the countable additivity, you do the same thing. Then you will be able to prove that out of that union, exactly one of them, exactly one AN complement is finite. And then do the similar thing. I
Yeah.
think you can do that, right?
The other one was let X be a set and A be an algebra.
Okay.
Let X not be fixed for any set A which is in the collection A. Define mu A is equal to 0 if X naught belongs to A. I'll go slow. And mu A is 1 if X naught.
Not
The first one is that X naught does not belong to A.
Okay.
Yeah. Show that mu is countably additive.
Okay. So see, this one is simpler than the previous one, right? So suppose we take an, a sequence in A, which is mutually disjoint. A intersection AM is empty. Okay. So there are two possibilities that either X naught is inside this union or X naught is not inside this union, right?
Yes.
If this is the case, the first one would imply that measure of this union, this is zero.
So when mu naught does not belong in the union of ANs, it is 0. That's because we've already
That is
defined.
the
Yeah.
definition, right? Yeah. But X naught is not inside the union also means that X naught is not in any of the ANs,
Yes.
right? And this would further imply that this summation of new ANs, this is zero.
Yes.
So at least in this case, we have that countable additivity.
This one's so much easier now that
Right,
compared
right.
to the other one.
So, but in the second case, what happens if X naught is inside AN? X naught is inside one of the ANs, right?
Yes. It's
For some N. But ANs are mutually disjoint, so it cannot be inside any other AN.
so it has to be in one particular AN. So which basically means that okay.
Yeah.
Let me just
So
copy.
I will share these notes right later. You need to write it down.
Okay, that's fine because I was actually playing around with this and I got really confused.
Yeah, this the accountability of this is very simple. You really don't have to worry much. So, like one of the ANs contains X naught, all other ANs do not contain X naught. So their
Mhm.
sum is one, and AN this is one, and mu of this union is anyway one.
Oh, that's because we've already said that n is a sequence of subsets in the algebra A such that the disjoint. So no n,
Right, right.
and so it has to belong in just one an. If I
Exactly,
do the
exactly.
union, it doesn't matter if, like it doesn't matter if it's countable or if it's like if I'm taking the union up to infinity, the the additive the countable additive property would entail that mu of am is 1 because it's disjoint. It has to be in one particular an.
Exactly, exactly. So for countable additivity, we require disjoint union, right?
Yeah.
Mutually disjoint union, in fact.
Count.
Okay, so now that you ask it, it is good because I think there was another question after this, right? We have to do something about the outer measure of this thing.
Yes, yes.
So have you tried that as well? Because I was going to discuss that outer measure question in today's session.
That
It is
would be
good that you asked.
I was I think it's a good segue, but if you can show that, that would be great.
What was the question? Would you recall?
So the outer measure was show that mu a, so mu star a is either 0 or 1
Mm-hmm.
for every a which is a subset of x.
Correct. So mu star A is always either 0 or 1. And was this the only question?
Yes, this was the only question. I think this was the extension of the
Uh,
question,
oh, okay,
and we
okay,
had to show
okay.
that mu star a is equal to 1 if and only if x naught belongs to a.
No, that is not if and only if condition. Like there was another condition to it because that condition I wanted to discuss today. Anyway, let us see this one. That mu star A is either 0 or 1, right? For
Yes,
every subset A.
yes.
So let us see why this happens. So you start with any subset A. What is mu star of A? Can you tell me the definition?
So mu star of a is infimum
Mm-hmm.
uh, of sub of infimum of summation of all the measures applied on any an such that
Yes.
an I'm saying an over here. I know he used a different definition. No, no,
It is fine.
he
A,
such that uh, such that such that a subset E is belongs in the cover of all the ANs.
So basically, this ANs cover A, right?
Yeah.
Yeah. And these ANs must come from the algebra.
Yes.
Okay. Right. Now, see, you start with any x. What about mu star of x? What can you say about this?
Of a singleton,
No, no, x, the whole space x.
the whole space X would be 1,
One,
right?
right? Because the measure itself is one, the
Yeah.
outer measure is one. So can we say that mu star of A, this is always less than or equal to 1?
Yes.
Because mu star is monotone and
Yeah.
A is a subset of x implies mu star A is less than or equal to mu star x.
Yeah.
Okay. So at least I know that mu star A is inside this interval 0, comma 1.
Yes.
Now I have to prove that it cannot take any other value other than 0 and 1. Right? Okay. So what can you say about mu star A plus 1 by 2? Can I say that this is bigger than mu star A?
Yes. Again, I can.
Because
Can
this
I?
is the, yes, we can. Because this is 0 and this is 1. Suppose that this is mu star A. Then what I am saying is you add them and divide by 2. So this is the midpoint, right?
Okay. Yes. Yes.
So it is bigger than mu star A. Okay. Now, and this is definitely less than 1. This is bigger than 0. It doesn't
Yes.
matter. So notice that this is the greatest lower bound of a set. Of some set. And this is bigger than the greatest lower bound. Therefore, it cannot be a lower bound, right?
Yeah. Yeah. It's not the lower bound.
If this is not a lower bound, it means what? There is an element of this set which is still smaller than mu star A plus 1 by 2,
Mhm.
right? So therefore, there is a covering AN such that it covers A, and this sum of measures of AN, this is say strictly less than mu star A plus 1 by 2. And of course, it is bigger than the measure,
Yeah.
correct? Yeah. Okay. Moreover, yes, and this is say less than 1. Also see, since mu star A is strictly bigger than 0, this implies that x naught is inside A, right? Can we say this?
If it's not 0, then yes. Because
Because
that's not
if
measurable.
x naught is not inside A, then this measure is 0, right?
Yes. Yes.
I mean the outer measure is 0. Therefore, if bigger than 0, x naught is inside A, which means x naught is inside one of these ANs, correct?
Yes.
Okay. But what would this mean? This means that this sum is at least 1, isn't it?
Yes. Because it belongs in at least one of the covers.
Correct. So one of the ANs it is in, so this sum is at least 1. But here we are claiming that this sum is strictly less than 1.
It's a contradiction.
So this together cannot happen. And why did this contradiction come into picture? Because we assumed that mu star A is neither 0 nor 1.
Oh.
Right? So the only way, like the only possibility for mu star A is either 0 or 1. This is what, this was the question, right? That mu star A is always inside this either 0,
Yes.
1.
Yes. Show that mu star A is either 0 or 1 for every covering A, or rather
Right.
every A in the subset.
Hmm.
So
Uh,
we basically took the assumption that the false assumption
mhm.
that suppose mu star A is not equal to 0, and mu star A not equal to 1. Okay. Yes. Thank you so
So
much.
is this clear?
Yes, it makes a lot more sense now. I completely did not consider proof by contradiction. I was like, how do I do this?
Okay, okay.
Uh, Anirudh, I was just hoping that if you could explain measurable sets like the extension theory and those things just a little bit. Uh, that would be great.
In like, what do you want me to explain exactly? Because if I start explaining everything, then
Just so basically, what extension theory? How can we define? So okay, give me 1 second because I'm going through
uh-huh.
the properties of measurable system. Um, is measurable. So S star, which is an algebra of X, and it has mu star defined on it.
Okay.
I was just wondering how we can use that to come up with measurable mu star measurable sets.
Mu star measurable sets. Okay,
Yes.
see, uh, it doesn't really require a star algebra. You take any, like any algebra, suppose, because we require that countable additivity and all.
Yeah.
Suppose A is an algebra
Hmm.
and mu is a measure on an algebra. So first question is, so see, this is our say universe X. Now there are some special sets which I can measure.
Yes.
There is some process by which I can measure. I ask a question: what happens if I take some this kind of a set, which is not in an algebra or on the algebra? Therefore, I don't know the method of measuring it. But
Hmm.
can we do something to measure it? So one of the natural things to do is let us cover this using elements of algebra, and then let us approximate it. So perhaps the covering may be too large. For example, whole of X is a covering, right?
Yeah.
So that is a very crude estimate. That at least I know that the measure of this pink box, it cannot exceed the measure of X,
Yeah.
right? But then I need to shrink it down. So suppose I take this new purple covering of this pink box.
Hmm.
So from this diagram, at least it is visible that I still
Yes.
need to shrink it down, right?
Yeah.
So till what point should I shrink down? So for that we require the outer measure in that way. So mu star of a set A, this is the infimum of, you collect all those mu ans such that these ans cover A and an come from algebra, right?
Okay.
So now this gives us a function on set of all sets. Now what we expect is that, suppose, let me zoom it in. So we have this thing. This is our set A, which we wanted to measure.
Hmm.
We expect that if we have something from the algebra, something like this,
Hmm.
let us call it as E, then this, what is the way to measure? I know that E is inside algebra, therefore E complement is also inside the algebra, right?
Yes.
So the proper way to measure is, let us measure this part, because here I expect that I know the method to measure it using mu, and let us measure the other part using the complement. So I expect that this red shaded portion and green shaded portion give us the whole measure of A. That is
Yeah.
what we expect. So if mu star of A is equal to, what is the red shaded portion? It is the common points of A and D. So A intersection E plus this green shaded portion is all those points of A which are not in E. If this happens, then I say that A is measurable.
Yes.
Okay. So, but this A difference is basically A intersection E complement,
Yes.
right? And then I just collect all these sets S star. I say that collect all those subsets of X such that mu star is, oh yeah, so here everywhere it is star. mu star A intersection E plus mu star A intersection E complement. And I call these measurable sets.
I had a question.
Yeah.
So is S star? Can we create an algebra, and on top of that, can we create a sigma? Can we define a sigma algebra on top of S star as well?
But S star itself is a sigma algebra, right?
Yes, I wanted to see that proof. I'm really sorry about that. I wanted to know how we can prove that. I know that it's a pretty. I don't know whether the professor asked us to do it, but if you have
So
any,
it is included in one of the lectures.
the proof.
Yeah, the proof that S star is an algebra, it is included in one of the lectures.
I think I asked a question. I think it was
Yeah, you asked through mail, but
I think it was one of those questions. I'm looking. I ordered Professor Rana's book.
uh-huh.
It's gonna take a bit of time, so I'm just waiting for it to come through.
Okay.
Hopefully it'll be there.
Yeah. Well, I would suggest you go to the lecture because the proof that this S star is algebra or in fact a semi-algebra, it requires a lot of work.
I know. I think it's a
So
it's a it's a it's Y intersection E1
yeah, for
union.
that, for
Uh,
unions, yes, for
yes,
unions we require
it
something.
was a pretty big derivation, and I was like, wait, where did this come from? The other thing that I wanted to ask was about the extension process. I
Huh.
absolutely did not understand anything about the extension process. Like I understood, it's just that I just didn't understand how we can extend from let's say any sigma algebra defined on an algebra all the way to S star. So if S is an algebra that has been defined on if S is a sigma algebra that has been defined on an algebra, how can we extend it to S star? Is it through this process that you just explained?
But yeah, it is through this process. But if you already have an S star, which is a sigma algebra, where do you have to extend it further?
Uh, no, I'm saying that if we suppose we don't have S star. So
Okay, we
suppose
don't have S star. Okay,
we don't have S star. We only have a sigma algebra that it has been. We only have an algebra. We can
uh-huh.
define a sigma algebra on an algebra, and
Right,
we have that. We have a up until a sigma algebra. Is
correct.
it possible to then extend that sigma algebra S to S star?
Uh-huh.
That's what I was going to ask, and I think that that's what you just showed over here. Is that let's
Yes,
suppose we
yes. This is exactly the process to extend that measurement.
okay. That I think that was about it for me.
Uh-huh.
For,
So see,
for,
there are like some intuitions are to be followed. One of the intuitions is that if we don't know something how to measure it, then let us take a cover and measure that cover. Then let us shrink that cover. That gives us outer measure. The second intuition that we should follow is this: that we expect that the measure, whatever way we measure, this red shaded portion and green shaded portion should give us the entire array.
Mhm.
Right? So if we just follow this thing, we get a star.
I heard the other one that I had was about the symmetric difference part.
Symmetric difference, yes.
So what's actually happening with the symmetric difference is that are we saying that that if I were to basically define a an outer measure on let's say f epsilon and e,
Okay.
then
No, actually, symmetric difference of what though?
so symmetric
We
difference of
require two sets, right?
yes.
Uh,
So f and so there's f epsilon which is one set, and there's e which is the other set, and they have an intersection.
acha. So they are not contained in one another, right?
No, no.
Okay. So say suppose this is the case, one is F epsilon and other is E.
Yes.
Yeah. So what are we saying now?
So the intersection between f epsilon and e is the symmetric difference.
No, it is a complex. See, symmetric difference is what? This, right? This union, this.
Wait, I thought it was the one in the middle.
No, no. See, E symmetric difference F epsilon.
Mhm.
This is what? E difference F epsilon union with F epsilon difference E.
Oh,
So we are collecting all those points which are either exclusively in E or exclusively in F epsilon.
oh, okay. I got it completely other way around. I'm sorry.
No, no, no issue. So, yeah, I think this is one of the required for one of the equivalent definitions of measurability, is it?
Yes, yes, exactly. So I think we had to show we had to take an epsilon definition.
Uh-huh. So we have to show that this outer measure of E symmetric difference F epsilon is say less than epsilon.
Yes,
This is what
yes,
we have to show, right?
yes. I think the proof was quite straightforward. It's just that I got confused over there
Okay, okay.
because I was like, wait, where is this coming from? Because I had absolutely no idea what the symmetric difference definition meant.
So this is the definition for us.
F epsilon and E. Given epsilon, right? Okay, that I think that suffices it for this week. Thank you so much. I'm sorry about that. The
Okay.
first problem was probably the one that was the most problematic.
Right, right, right. Yeah. It actually required some technicality here. It was a small technicality, but yeah, that observation was important.
Yes, because you know that part where A union B complement is it's either A
Finite. Yeah.
complement is it's A complement is finite or B complement is finite.
Yeah. And both of them cannot be finite together. That is
And
the
exactly.
main takeaway from all this proof.
Um, and here just a quick question was about the
Mm-hmm.
probability space. So
Uh, yes.
so with the probability space, uh, so a measure space is always made up of three elements, right? You have
The universe,
the
the sigma algebra, and the measure by which we can measure the set.
can it be can it does it have to be a sigma algebra? Can it be an algebra?
By definition, we usually take sigma algebra because if we have a sigma algebra, then that countable unions and countable intersections are already inside of it.
Okay,
So for countable additivity, we don't need to worry whether the union is inside the set, the collection or not.
okay. And the probability measure is just a special type of measure.
Yeah, that measure is whenever the measure is between 0 and 1.
Okay,
On any
so
space.
measures can be so the only thing about a measure has is that it has to be finite, right? Like you cannot have the
No, why? The Lebesgue measure is infinite, right?
I haven't done Lebesgue. Sorry.
Oh. See, the length function,
Yeah.
length function is the Lebesgue measure. The length of the real line is infinite.
Oh, yes.
It can be infinite. It need not be always finite.
But when we say that mu has to be finite, what do we mean by that then? Because mu is a measure, right?
Yeah, it means that if we are saying that mu is finite, it means for every subset the image is the value is finite.
Okay.
Let me just write it. Finite measure means this is some collection to 0 infinity measure such that for each a mu a is finite.
Oh. Oh. Okay.
Yeah.
So sorry about that. My I thought that the function itself had to be finite. Sorry about that. Okay.
No,
That makes
but
sense.
so this is the definition of finite measure. And in general, measures need not be finite. For example, the length function, it is not a finite measure.
Yeah. Yeah. Okay, thank you so much. I'm sorry for asking so many questions.
No, no, it is. That is why these live sessions are conducted. So it is good that you ask so many questions. So
I'll
actually,
probably be sending a lot more emails because
no, I couldn't hear you. Could you repeat?
I usually make a lot of comments, but like when I don't understand, I usually make a lot of comments. So I know you get a notification every time, probably every time I make a
Yes.
comment.
Actually, some things I cannot explain through mail because it is tedious to write and then send. So it is better to discuss in person.
Yes, yes, it is. I'll probably this was about it for me. So I'll probably take leave. But if I have any more issues with the week 5 contents, I'll probably send you an email. I probably
Yeah,
won't have
please,
that many
you can do
issues,
that.
but hopefully next
Okay, sure,
I'll
sure,
probably send you an email if I have any issues.
sure, 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 sure.
Thank you so much, Anju. Thank you.
Okay, okay. No worries. So actually, in this thing, I wanted to discuss uh, one more exercise was in continuation to this measure, right? That we had to prove that whenever x naught is inside A, this was the exercise. If the singleton x naught is contained in A, then mu star A is 1 if and only if x naught is inside A, right? Uh, okay, Robin left, I think. Okay, so let us just quickly see this. So suppose that mu star A is 1. If mu star A is 1, then what it means that this infimum of this set is 1, right? A is contained in this union AN coming from this algebra. This infimum is 1, therefore all of these are 1. For every covering AN with A contained in this union, this sum is 1. Okay. But this sum is 1 would imply that, uh, you know, from here we say that x naught is inside AN for sum n. Okay, in fact, this n is unique for some, or rather, I should directly write for unique n. What happened? I am not able to write for a unique n. Now, see if x naught is not inside A, then this AN union AN difference x naught, this covers A. Right? But this sum now would be summation ANs, sorry, mu AN, where m is not equal to n, plus mu of AN difference x naught. Now this is 0, which is not 1. That is a contradiction to the previous assumption. So yeah, and if x naught is inside A, then that is the easier part because every cover must have x naught inside of it, and therefore the sum is always 1. So, okay. So this is one thing. Prasanjit, do you have any other questions?
Yes, sir. This exercise I have done,
Uh,
but I have a little query from assignment.
okay.
If you allow, I can tell
Yes,
that
yes. Tell me.
if there is a set defined x is equals to left open right close interval 0 1
Okay.
intersection rational numbers,
Uh-huh.
and there is a algebra generated by left open right close intervals in R.
Oh, sorry. Left open, right closed intervals in R or
Algebra
in X.
generated by left open right close intervals in R.
Okay. Uh-huh.
So i- in in the set X intersection algebra A,
Okay.
there is non-empty countably finite sets, whether it is true or false. In this
Yeah.
set, non-empty countably infinite sets. So
No, it is
I
not true.
think it is true, but
No,
the
why
answer
is
is
it
false.
true? See, what is X intersection A?
So from every element in A, we intersect with it in X.
No, 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 that is not the case. This is the algebra generated by the left open right closed intervals inside X. Algebra generated by left open right closed intervals in X, right? Hello. Yeah,
Hello?
Prasandeep, do you
Yes, sir.
understand this?
Internet
This X
problem now.
intersection is. Yeah, can you hear me? Hello.
Hello?
Tell me.
Okay, okay.
Yeah, yeah.
Algebra.
I
Okay,
was saying that X intersection A is the algebra generated by left open right closed intervals in X,
okay.
right? So why does it have to be countable? This is uncountable, right? You can sort of prove it.
Yeah, yeah. Get I get it wrong actually. X intersection. Yeah. Okay.
Acha, how will you prove that this is not countable? Have you thought about it? Prasandeep,
So it contains left open right close intervals with endpoints
in rationals,
rationals.
correct. So, you have to work a bit because there might be something. Uh, what you need to do is, see, I will just give you one hint because it is really out of the scope of at least today's discussion. We can discuss it sometime later. You can try doing this for every subset I of n. Uh, we can find this a set bi inside of x intersection a, and if I is not equal to j, then bi intersection bj is empty. So you just try doing this.
Okay, sir. I will try.
If you are able to do this, then it is direct that the algebra is contains
So
uncountably many.
for every subset, I is contained in N, and we can find B1 belongs
Bi.
to
I mean,
B.
corresponding to every I, you can find a bi.
And if I not, what is if I not equals to?
J. If I is not equal to j, then bi intersection bj is empty. You try doing this. If you are
Okay,
able to do this, then you can directly say from here that this x intersection A has uncountably many elements.
okay.
So, any other question?
No, sir.
Okay, so I guess perhaps we can stop here for today.
Okay, sir. Thank you.
So any questions from the online audience of YouTube? No. Okay. Fine. Okay then. Thank you everyone. We'll meet next Friday.